In this video, we're going to go through the solution to the Dirichlet problem on the disk. The theorem we have here says that we start with a continuous function g on the unit circle, and then we build this function u here using the Poisson integral inside the unit disk and using g on the boundary. So u will just be defined to equal the Poisson integral inside the disk and equal to g on the boundary. And then our claim is that this is continuous on the closed disk. And we've already shown in class that this is harmonic on, I should say, the open unit disk. I don't know why I have boundary there. Harmonic on the open unit disk. So the argument we use is a pretty standard one, but it's you may not have seen something like it before. It's called an approximate identity argument. So the Poisson kernel, recall, is written like this in complex notation, where we have z in the disk and w on the circle. Poisson kernel has three key properties. It's non-negative. You can just see that from the formula. It's integral on the unit circle, or its average on the unit circle is 1. And we saw that last time because it reproduces harmonic functions. So it reproduces the function 1. And then what's a little less obvious, but we'll do it with a short computation, is that if you fix a delta greater than 0 and make w that distance away from 1, then the Poisson kernel goes to 0 uniformly as r goes to 1. So it's uniform in w's that are a fixed distance away from 1. So this property is less obvious. It requires a little bit of a computation. So here's the computation. We need to look at the denominator in the Poisson kernel, which is this, 1 minus rw all squared. If you just square it out and then try to kind of separate out the 1 minus r portion, you can eventually get to this nice form, which shows you that the denominator is small when both r is close to 1 and w is close to 1. But notice w is on the circle, but r is a real number between 0 and 1. Okay, then straight from this, the Poisson kernel is less than or equal to this quantity when 1 minus w is greater than or equal to delta. And so this part here protects the denominator from going to 0. And so if I send r to 1, the top goes to 0, and this goes to 0, but the bottom stays bounded below. So the whole thing goes to 0 uniformly with respect to w's at a positive distance from 1. So these are the three key properties that we use of the Poisson kernel in the next argument. Okay, so let's prove the theorem. Let me move the theorem statement next to it just so we have it handy. Let me rearrange this a little bit. Okay, so here's our theorem. So to begin the proof, let's just take z, a point on the unit circle, w on the unit circle, and then r between 0 and 1, and we want to compare u of rz, so rz will be an arbitrary point in the disk, to u of w, and we need to show that this goes to 0 as this point in the disk goes to w on the circle. And it's actually enough to show that u of rz goes to u of z as r goes to 1, since the boundary function is already continuous. So u of z goes to u of w as z on the circle goes to w by continuity of u on the boundary. So u is assumed continuous on the circle. So we just have to deal with these sort of radial limits here. So we have to dig into the estimates. So let's look at u of rz minus u of z. We can express u of rz using this formula here, using the Poisson integral, and I've written it using a d theta here, so you get this term. And then recall that z is just e to the I alpha, and I can express just this constant as a Poisson integral since the integral of the Poisson kernel is 1. So here I'm using 2 to bring this constant inside the integral, and that's important for comparing u of e to the I theta to u of e to the I alpha. And then I just bring absolute values in, and the Poisson kernel remains unchanged because of property 1, which is just that the Poisson kernel is positive. Okay, and now I guess I did a little bit of change of variables here that I forgot to mention. The Poisson kernel at Rz evaluated at e to the I theta really is the Poisson kernel at R evaluated at a shifted point on the circle. And then you can replace theta with theta plus alpha to get the Poisson kernel here by itself, just depending on R and e to the I theta, whereas this part, when you do that shift, we'll get an e to the I theta plus alpha there. And now I'll shift to an arc line, an arc length integral here. It's just a little more convenient for what we do next. So now we'll integrate with respect to zeta on the circle using an arc length integral. And so this is just notation. But now we're going to split up the integral into two pieces. So the region where zeta is within delta of 1, and the region where it's away from 1 by a distance of delta. And delta will just be a fixed positive number that will change later. But the first integral, when I have zeta close to 1, well, if zeta is close to 1, then then zeta times z will be close to z. And so if you compare these numbers, z has modulus 1, so this distance is just the distance of zeta to 1. And so you can bound the inside just in terms of this quantity here, which is the supremum of the difference of u at 2 points that are within delta of each other. And now this no longer depends on z or r. This is just something called the modulus of continuity of u, and this has to go to 0 as delta goes to 0 because u will be uniformly continuous on the circle. But we don't want to send delta to 0 yet because we have to control the Poisson kernel, or we have to control this term when zeta is away from 1. So to control that term, well, you just bound u by its supremum on the whole circle, but then you look at the Poisson kernel when zeta is away from 1, and property 3 of the Poisson kernel said that this part tends to 0 uniformly as r goes up to 1. And so we'll send r up to 1. You can do that taking a lim sup of our difference in case we don't know that any limits exist yet. So we take the lim sup as r goes up to 1 of this difference. This part will go to 0, and then you're just left with this expression here, which doesn't depend on anything anymore except our made-up parameter delta. So then you can now send delta to 0, and this expression goes to 0 as delta goes to 0 because u is continuous on the circle. So that proves that u of rz goes to u of z as r goes to 1. And again, we already said that then if you need to estimate this difference, well, you could send r to 1 and then z to w. But we do get the theorem that we wanted, that this expression is continuous on the closed disk now, and we already showed that it's harmonic on the open disk. So that solves the Dirichlet problem on the unit disk.